Hi, my name is Jessica Beach. We were given the molecular formula of C7H14O2. The degree of unsaturation can be found when we use the formula C minus H over 2 minus X over 2 plus N over 2 plus 1. For this compound, the degree of unsaturation is 1. This means the unknown compound is either a double bond or a ring. Looking at the IR spectroscopy, we can identify the functional group and the purity. While we can't get a definitive purity level based solely off of the IR spectra, we can get a general idea. Looking at this IR spectra, we find a sharp CO double peak in the 1740 region. This is typical of an ester. It can also be an aldehyde, but there are no CH stretches at the 2850 and 2750 region. We can also see strong CO stretches in the 1200 to 1300 region. This is typical of an ester. In the 3000 region, we can see a normal sp3CH stretch. This confirms that the unknown compound is an aliphatic ester. We can also note that there is an absence of an OH group in the 2500 to 3300 region, eliminating the chance of the compound being a carboxylic acid. We can see that there are no other strong absorptions. This would suggest a high level of purity. When looking at the 13C NMR, we can find the number of signals and chemical shift. This gives us an idea about the carbon framework. In this given 13C NMR, we find 6 distinct carbons. The given molecular formula shows 7 carbons. This means that one carbon environment is repeated. The data shows 1 ester carbonyl, 1 oxygen substituted carbon, and several alkyl carbons with symmetry. When reviewing the 13C NMR, we find the following signals. 170 ppm is a CO double bond, an ester. 82 ppm is a CO bond, a tert-butyl. 32 ppm is a CH2 between O and a substituted carbon or substituted sp3 carbon. The 22 to 25 ppm signals are CH3 groups, and the 9 ppm signal is a CH3 further from the carbonyl/oxygen. The 13C NMR provided allows us to deduce that the compound is an ester with an OCH2 group and a CCH3 group. The 1H NMR allows us to find how many types of hydrogen environments exist, how many hydrogens are in each environment, integration, and how the hydrogens are connected, splitting patterns. Here we see a signal at 1.2 ppm. 9H gives us 9 equivalent hydrogens. This is indicative of 3 equivalent CH3 groups. We also see that it is a singlet. They are attached to a carbon that has no hydrogens, quaternary carbon. The 2.0 ppm signal is a 3H, which means 3 equivalent hydrogens. The methyl is directly attached to a carbonyl. It is also a singlet. The 3.9 ppm signal is downfield. This is a CH2 attached to an oxygen. It is a singlet and has no neighboring hydrogens on the adjacent carbon, quaternary. The information provided corresponds to a tert-butyl group, an acetyl-methyl, and an OCH2 group. The integrations match the expected 14 hydrogens given in the molecular formula. The absence of splitting indicates attachment to a non-protonated or quaternary carbons. Given the information from the H1 NMR, we can deduce the structure. The 9H indicates 3 methyl groups attached to a quaternary carbon. This gives us a tert-butyl. To the left of the structure, we can draw 3 methyl groups attached to a carbon. This aligns with the 9H. The 2H is a methylene group attached to an oxygen. The singlet multiplicity suggests that the adjacent carbon is quaternary, has no carbons to couple with. The 3H is a methyl group attached to a carbonyl. It is also a singlet, which means there are no adjacent carbons to couple with. The collective information provided shows that this compound is neopentyl acetate, IUPAC name 2,2-dimethyl 1-propyl acetate.